All right, so we're ready to continue with thermal sensors in this course on CMOS MEMS. And I discussed this micro-machined thermal sensor, micro-Pirani sensor, or micro-Pirani pressure gauge, as pressure sensors are also called, the pressure gauge. So and this is one way to write it. Some people, they hear gauge and then they write gauge. I think it's less correct because gauge comes from the French jauge. Jauge, it's kind of Eichstab in German. So sorry, pressure gauge. Yeah, and so we saw yesterday that this object conducts the heat that is generated in this heating meander, this resistor, via two channels, namely the suspensions or the support, which is in this structure. Actually, it's this radial part. So heat is transferred here horizontally from the heated region to the support where there is temperature T0, all around those segments where the membrane is fixed on the side, clamped to the substrate. And then there is the second contribution that has a much stronger, actually, that has the gas pressure dependent conductance, which is across this micro-machine gap. And this micro-machine gap, I haven't told you explicitly. Again, you should implicitly know from chapter 2 that if we remove metal 1, this is probably in thickness T, gap. This T gap is likely something like 0.5 to 1 micrometer. I think in this process was 0.65 micrometers. So this is very small. And when you think about, so 650 nanometers, when you think about the collision, the free mean path of the molecules in air, which we mentioned to be around 100 micrometers, then it's not so far away from the Knudsen regime transition from bigger to smaller, or smaller to bigger than 1. Imagine the pressure to go down by a factor of, let's say this is 0.5 micrometer, 500 nanometers. So let's let the pressure go to 1/5 of an atmosphere. Then the mean free path increases by a factor of 5. Because the density of the molecule is 5 times as low, and the molecule on its track has a 5 times reduced chance of hitting another one. So at that point, the mean free path will be increased from 100 nanometer atmospheric pressure to 500 at this reduced pressure, 500 nanometers. So at 1/5 of an atmosphere, we'll have the transition from continuum thermal conduction to collision, molecular transport mediated thermal conduction. And that has been modeled, please remember, intensively in this early part of the chapter, in this preparatory part where I talked in some length about, where is it? So it's about here. It's thermal heat flux. It's proportional to the delta T with some parameters that depend on the collision length. And so you can, of course, they depend on the density and therefore they depend also on the pressure. And this is what is at work in this sensor. So you can imagine that, where is it? So that at room pressure, this sensor has a certain horizontal and vertical conductance, which is given by the continuum heat transfer through the dense gas in the gap. And if you increase the pressure to higher pressures, this gas contribution will remain constant because it is independent of pressure. The pressure increases, there are more molecules, but they conduct less far. They have a mean free path that goes inversely proportional to the density, and the kappa is constant. And therefore, there is no pressure sensitivity from room pressure to higher pressures. But as you go down into reduced pressures, 1/10 of an atmosphere, 1/100th of an atmosphere, 1,000th, then you will see an effect. Then the transition from continuum thermal transport to molecular thermal transport will become apparent. And the molecular thermal transport is proportional to the density. So it reduces very strongly, and that's what we see in the characteristics. So let us look first at the graphs on the right. So here we have 3 curves corresponding to 3 different sensors. This one with 200 micrometer diameter is the one that you see here. Okay. So the thermal conductance in microwatt per Kelvin is a function of pressure, no doubt. And it does what we expect. It essentially saturates and becomes constant at high pressures. This is at 1 atmosphere, 10 to the 5 Pascal. So, well, it appears that actually it's not yet fully developed. Much smaller than 1 regime. So there's an amount of contribution of molecular, while we are right in the transition, so to speak, and then at 10 atmospheres, definitely, this is like continuum transport, and then as the pressure is reduced, well, this contribution by the gas becomes smaller and smaller. Now, the pressure is on a logarithmic scale, the conduction is on a linear scale, and what you also see is that it saturates at some value. So let's say this is the lower saturation level, and what does that correspond to? That is the limit where the gas doesn't conduct anymore at all. There is an insignificant number of gas molecules present to conduct heat, but there is still the material conducting horizontally this electrically dissipated heat away to the substrate. And that contribution is visible by this constant. It cannot be exceeded, subsided, it cannot be unterschritten in German. That's the minimum. And then on top of that, there is on top this pressure-dependent gas thermal conduction, which makes this characteristic S-shape. And this S-shape is characteristic of all thermal pressure sensors that exploit the thermal conduction of gas. The macro-Pirani sensor does the same. But it's much larger. This object here has maybe a centimeter or a few millimeters of diameter. It's instead of let's say 5 millimeters, instead of 500 nanometer, it's 5 millimeters. Half a micron. My God, too complicated. 10 to the minus 6. That's micro Pirani, and then conventional Pirani is 5 millimeter, 5 times 10 to the minus 3. Okay, it's a factor of 10 to the 4 larger. And therefore, the pressure at which the transition occurs from continuum conduction to molecular conduction must be at a much lower pressure. The pressure must be a factor of 10 to the 4 smaller until the mean free path of the molecules becomes 5 millimeters. And that means that if this were a sensor of macroscopic dimensions, I'll draw just any curve here, it would have some saturation value, and then roughly 1, 2, 3, 4 powers of 10 later, it does its transition from one level to the other. So macroscopic pressure sensors are designed to measure vacuum pressures. This is where the Pirani sensors are at work in vacuum chambers at 10 to the minus 5 or 10 to the minus 6 atmospheres. And that's where they are good. And there is a range of maybe 3 or so powers of 10 of pressure where they are good before they saturate at the other end. And that is a characteristic of all thermal pressure sensors. And you see that at work also in this micropirani. It's just shifted to higher pressures because it is smaller. Now you can extrapolate this to the invention of other sensors. If this sensor had a gap of 50 nanometers, then this whole curve would be shifted a factor of 10 towards higher pressures. And if it was 5 nanometers, it would be 2 of those. Yeah, then you can high pressure sensors, high pressure thermal pressure sensors. Yeah, with nanometer gaps. Yeah, that would be maybe a first. You know, for the first time we have blah blah blah. Yeah, as scientists are. So this transition point is characteristic to dimension. It's a direct implication of the dimension. And the fact that we can have a sensitivity around room pressure changes around room pressure. So if the air pressure changes because a weather front comes and the pressure drops, we can measure that with the sensor. And if we go up the mountains to Mont Blanc and reduce the pressure by a factor of 2, then we go from 10 to the 5 roughly to 5 times 10 to the 4. Yeah, there is a pressure difference. So the sensor, such a sensor is at these dimensions is potentially a barometric pressure sensor. Okay, and that's what we thought. Yeah, my colleague Andreas Heberli and I designed a system. Actually, there is a second graph here that I can also show. So what you see here is the current, the resistance change of the sensor. So this resistor R, this resistance nominally has the value R, but then because we are sending a current through, of course, it experiences some delta R due to the delta T, due to the temperature increase. But the delta T is proportional to the power that we dissipate, the heat power dissipate, the electrical power, and that is proportional to I squared. So the resistance change delta R is proportional to I squared. If I send a current through in one direction or in the other direction, it produces the same effect. Not sending a current through doesn't heat, a current heats, and that means that this curve has to be parabolic, and it is parabolic, by this ohmic heat law. You see that delta R over R0, the resistance changes by %. And if we introduced here the temperature coefficient of resistance of aluminum, the resistive material, we could calculate the delta T. And because it is 0.3% per Kelvin, I would assume that this corresponds to about 3 degrees, delta T around 3 degrees Kelvin. It's an estimate. I may be off by a power of 10. It was a bit fast. Please calculate that, verify that. But it could be. So that at 5 or 6 milliamp sent through that aluminum resistor, at 1 megapascal, we obtain a temperature increase of 3 Kelvin. So that's what we need to heat to reach 3 Kelvin, because at these 3 Kelvin, the power dissipated by 6 milliamp will be dissipated horizontally by the supports and by the gas. If I now decrease the pressure to 100 Pascal, in order to reach the same temperature increase of 3 Kelvin, I need to heat much less, namely 2 milliamps. Why? Because only the horizontal conduction is still there, and at 100 Pascal, there is virtually no gas conduction anymore. So to obtain the same temperature increase, I can have a much lower current. And so there is a way to translate pressure into a current information, because if I have a system that maintains the temperature of the membrane constant, independent of pressure, so it adjusts the pressure by putting more or less current so that the temperature is constant, that current varies with pressure. And the current is then the measure of the pressure. The current says how much the pressure will be. I have to calibrate that, of course, but it will be the information carrying the information about the pressure. And so the system that Andreas Heberli designed based on my sensor was kind of as follows. So you have a sensor resistance, RS. This is the meander on the membrane. And it is fed with a current I. And so there is this current IS that goes through the sensor. And then there is a second resistor, which is called RR, R for reference, a reference structure, which has a resistance slightly smaller than RS, maybe, 2%, a percent or so, or 2% lower. I can't remember what it was. But it receives the same current IS. And this is done by a design that electrical engineers, circuit designers use universally. It's a current mirror, two identical transistors that are operated in the same point. They must produce the same currents, and then the same currents go through these two resistors, and they produce a voltage, which let's say here is certainly smaller than the voltage here. No, sorry. This is I wrote it the wrong way around. It's slightly larger, or slightly larger than RS. So the voltage drop over RR is larger than the voltage drop over RS because RS is smaller. However, RS is also heated. So by sending a current of just the right level, RS heats up from RS plus delta R, due to the current IS, it heats up, and at some point the voltage drop over this complete resistor, this heated resistor, is equal to the voltage drop over the reference resistor. And because those two signals are the input signals of a differential amplifier, and this amplifier puts its voltage out as a control signal over the resistors, the system tunes itself automatically into this equilibrium where the minus and the plus are equal. So that this implies that the delta R is constantly kept, irrespective what other effects work on that sensor. The heat conduction mechanism, for instance, the relation between IS and delta R. This is the gas pressure, P gas. So irrespective of P gas, the voltage is constant. The voltage is constant. The voltage is constant, and therefore the delta R is constant. But so now this whole system also has a second branch where, let's say, I think that there should be also a current mirror. I wonder about this I2, and well, whatever it is, the voltage is also, or the current value is measured also. Current value is measured, and via a voltage drop. So essentially, one has a voltage drop measurement. V1 is being measured, and then Vs. Where is Vs? Vs is also measured, Yeah, so one measures the current IS, one measures the voltage drop over the sensor, and from these two informations that are extracted in these A to D converters, in these bit streams, one is able to basically extract the heating power, the electrical, I should say the electrical power, P electrical, that goes through the sensor. Of course, the current IS that is needed to reach that delta R, that to reach that delta R strongly depends on P gas. It's just the delta R that is constant, irrespective of gas pressure, but the current needed to obtain that. So these bit streams are functions of pressure. And then, of course, the electrical power dissipated is also a function of pressure. And you can look at this, at the structure itself, the system, the microsystem that you see here. This is the chip, about 2 by 3 millimeters large, and you see these sensors, here in the top part, and the circuitry that does this system component part in the lower part. You see 8 sensors that are here in series, so that let's say the total resistance of this structure is compatible with the voltages that are applied and the currents that flow through are reasonable, so that one has maximum signals, maximum voltage. One uses the voltage that is available at the system, the input, the VDD, and then so those are in series, and then there are reference sensors that are also in series, meandering through in a common centroid design, minimizing gradients of whatever, the effect of gradients and whatever on the outcome. And those reference sensors, you see, are just meanders as they are implemented in the thermally sensitive sensors, whereas here the meanders sit just on the silicon chip, embedded between the dielectrics, and there is no gap underneath. So they are in contact with the silicon. They represent temperature T0, whereas this represents temperature T0 plus delta T, implying that this has reference some resistance RF, and this has then RS plus delta R of delta T. So this is how these resistors were implemented, and what you also see is the beautiful shining structure here of this disc, which shows that in this optical micrograph, the aluminum is still visible. Aluminum 1 was not yet sacrificially removed. That was a chip photograph before micromachining. That's also what it tells you. And then I see more. I see these bumps here. They should be shiny too, because aluminum is shiny everywhere. They're not shiny. So these structures were elaborated or increased enhanced by gold bumps, as we already seen in other chips. Because this is a microelectronic chip that has this bumping service. And when you look at now the characteristics, so here we have again some outputs as a function of pressure that mimic what we already know. Some Vs as a function of pressure, which is a function, this S-shaped function, saturating, because the thermal conductivity saturates. And here the heating power was calculated based on Qi and QV as a product basically of the information they contain as the heating power, the P electric in the earlier slides, and that mimics very well the standalone characterization result of the sensor, which was obtained without circuitry. This is something which I just did electrically then, sending in some currents and trying to make the temperature constant, or measuring the thermal conductance, actually measuring the delta T for a given heating power as a function of pressure. So this is an early pressure sensor. Now you may wonder why is this pressure sensor, has this become a product or not? Frankly speaking, it is power hungry. Thermal sensors consume a lot of power, and microsensors are designed to be integrated in applications where not a lot of power is available. If you think of a watch with a pressure sensor to indicate the altitude or the change of the weather, you would like to have a pressure sensor that consumes as little as possible. And for that purpose, other principles are better suited. Capacitive pressure sensors, where a conductive membrane is deflected by a differential pressure, as we have seen in chapter 2 from Siemens or Infineon and other companies. Those are potentially structures that don't consume as much power, because measuring a capacitance doesn't require heat to be dissipated and to be lost to the environment. It just requires some charges to be sent back and forth, and then voltage to be measured, and that can be done much more moderately than dissipating heat. So the pressure sensor in your smartphone is not a thermal pressure sensor. But anyway, it was a good development, and we learned a lot about calibration and compensation of other effects. It was typically a compensating structure, where the background temperature of the chip, which is also not constant, did not play a role anymore, because the reference structure and the really sensitive structure were close to the same. Yeah, good. So now I have two more topics in this thermal sensors chapter, namely thermal converters and gas flow sensors. So what is a thermal converter? We'll find thermal converters in measurement devices for AC signals of potentially unknown frequency, or even superpositions of signals of unknown frequencies. So not the DC signal that you measure as the voltage of a battery to see if why your toothbrush doesn't work anymore. They have not batteries, but rechargeable batteries in there. But anyway, so time varying signals. And when you measure, the voltage at the plug, with the AC measurement mode, it gives you a voltage number. It says 220 volts. What does that mean? How many volts would I have to apply? Or how many DC volts would I have to apply to obtain the same result? For instance, making a light bulb incandescent. If I plug in 220 volts or plug in an equivalent DC volt. And thermal converters are designed to make that conversion. What is the equivalent DC power, the equivalent DC voltage that causes the same dissipation of power as this unknown AC mixture of signals? So the goal is, given a fluctuating voltage V of t and a sufficiently long time constant, let's just do an average. Actually, this is a moving average, starting at time t, going up to time t plus tau, and then averaging v square times t at these times in this interval. So if I have my time interval, and here is my time t, and then I have my interval t plus tau, and there is this signal v square. So let me draw the signal v, something like this. This looks like a fairly sinusoidal signal. And now I do the V square. This will be something like this. Yeah, approximately. And so I'm doing an average of this yellow stuff here, this V square T prime over that interval. Yeah, and then this interval is shifted along the signal, or the signal just moves along, and I do my measurement. Yeah, but it's equivalent to saying, okay, here is the signal, and move along with my time time interval. And so this average of the square. Actually, I have to divide that by tau. Yeah, so I have to do a division by tau. That's here. Yeah. So then we have the average V square, and then we take the square root thereof and call this the V, the average V. Yeah. And of course, this is a function of time. And this tau indicates that the integration time was tau. So V of t is a measure of the average power deliverable by Vt in a resistor, according to it's equivalent V tau square over R. It's the same as the V square of t over R averaged over time. Yeah, so this is a measurement problem that is solved by instruments, and well, young people like you who live in the digital era say, well, I only have to have an analog to digital converter, and then I do some calculation and I integrate those numbers and I have that. Yeah? But this is a power greedy procedure. Doing large calculations costs a lot of power. Yeah? Therefore, there's this tendency to do that rather by other methods. And so what one does is integrating with precision, summing up squared numbers and so on. And so what one does is one dissipates Vt in a thermal structure with thermal time constant. And if that time constant is large enough, if the Vt fluctuates large enough, the temperature of this thermal structure will be essentially constant, corresponding to the power, the average power that's being dissipated. And then one can have a similar structure, hopefully a similar microstructure that is fed with a DC voltage, and that will also heat up that other structure. And when those two temperatures are identical, then one knows that the Vt dissipates the same power on average as the DC voltage. So this is a control system that has to tune the structure into a working point where the two temperatures are the same. So when the control VDC has to ensure that whatever delta T is measured on one side and delta T is measured on the other side, they match. And so this is much simpler than an analog digital implementation, and such structures have been produced, in the early days by many groups, and they're now in instruments by Fluke and Hewlett Packard and so on. Agilent. Now it's called Agilent. This measurement business of Hewlett Packard. And so you see an early research result by Klassen from Stanford, a PhD student at Stanford. He produced these interesting suspended little microelectronic structures, that had a heater in them both, and they also had a diode in them to measure the temperature. So the diode measuring principle, this PTAT measuring principle, was also at operation here, so to speak, in a feedback loop that regulates the heating power on both sides to the same level. So here is this unknown input voltage, this AC input voltage, and then here is this DC voltage that is applied, that is produced by this differential amplifier, and then once the two nodes are at the same potential, then this difference is zero, and then well, the system is obviously in the working point that it needs to be in, and that output signal is the equivalent voltage. So this output voltage is equal to the average V square in square root. And so they used a CMOS process by a service that existed then, the MOSIS service, so university groups could address this organization, MOSIS, that had access to CMOS foundry processes and that took care of all the handling of the data files and compiling data files of different research groups on the same wafer, and then chips came back, and then Claassen and his co-author did anisotropic silicon etching from the front, and interestingly, they did TMAH etching, not EDP etching, as we did at ETH Zurich. So that was kind of an interesting point for us. They had some additives in there that made it sure that the aluminum would not be etched. So TMAH also works as a CMOS compatible etching, if you know what to add to it. And then also some silicon stayed here. Suspended was not removed. The silicon of the substrate was removed, but then we had some silicon islands down here. And so this was an N-well, like in these electrochemically etched pressure sensors that I mentioned, where the P substrate is removed until the membrane the N membrane structure is reached. And the etching stops there naturally because the charge transfer, electrochemical charge transfer can't operate anymore because the voltage, prevents that. So that is also work here. So while etching, they had one of those. They had the link to the contact to the N well under potential, and then this was spared from etching. And so they have a thermal resistance of 37,000 Kelvin per watt, or you can calculate the thermal conductance G thermal as the inverse of R, time constant of 5 millisecond, which means that they can measure basically at 200 hertz and more, and that's exactly what they produce. 200 hertz is just at the limit, and 1,000 hertz is certainly better, and then up to very high frequencies, well, reasonably high frequencies there. This is not a high frequency design, it's a medium frequency design, and they had very good nonlinearity and 60 dB of range, which is quite a few powers of 10 of range. So high linearity over a large range of signals, and the temperature measurement was done using these diodes that had some potential drop in this way of being operated. And there are other works in this direction from the National Institute of Standards, the University of Michigan, also Dominique Jacki, PhD student in our group at ETH Zurich, where I worked as project leader. I worked on that, and he also completed a PhD thesis. This was a structure that was on the basis of two membranes. So two membranes like the infrared radiation sensors that are membranes, but he had, of course, some heating resistor going through that membrane, and then thermal piles to measure the delta T. And through one heating resistor came the time fluctuating V in, through the other came the VDC, the direct current reference signal, and then by comparing the outputs of the two thermal piles, could again operate this as a thermal converter. He also did another version with one big membrane with two heaters, and then this was a more complicated control system. But anyway, that was okay. And as I said, Fluke has some voltmeters that implements such a thermal principle with micromachined thermal structures. And you see that I mean, the equivalent voltages are quite over a wide range. Yeah, so here is one example of the University of Michigan, also based on two membranes, two diaphragms, as they call them. So continuous dielectric layers with implemented resistors. Each of these membranes had 3 resistors, as you see here, that are used for different purposes. And there are some, so there's the one signal that comes in here that heats the membrane, and here is kind of a reference signal that does the same thing. And then there are some additional, heating, biasing signals implemented via the other resistors. Maybe this whole thing to operate in this stable, equal operation point. And as in all these thermal converters, the output signal is then the true RMS average of V in. Yeah. So last topic, thermal flow sensors. That's also an interesting topic that really took off and now is kind of standard in MEMS, in thermal MEMS. And let's say the principle implemented is that of hot wire anemometry in its many variants. Yeah, so hot wire anemometry is actually a simple thing. Yeah, so you have a flow of gas flow, and then you put into that gas flow. So here is some support, and then so very schematically you put in a hot wire in this gas flow, and then of course depending on the speed of the gas, the wire gets cooled more or less. So the power drawn away from that wire for a fixed delta T above the T0 of the surrounding gas, the power needed to maintain a delta T has so power electric as a function of flow velocity. Let's call that flow velocity. Yeah, that flow velocity going over this wire draws away power, and then one needs to, in addition to the P at rest, at air at rest, one needs to add a contribution that goes like a square root of V. So the power electric is kind of a P electric 0 plus some coefficient times square root of the velocity of the gas. Yeah, and this is called King's law, which is basically summarized in this formula here. I mean, square root functions are very ugly functions for sensors because they have infinite slope here, and then you're highly sensitive at small velocities and not so sensitive at higher velocities. Whenever you have an ideal sensor, you would like to have something linear. Linear output lets you correlate the horizontal axis much easier with the vertical axis. And so, especially since the square root is offset by this value here. So one design that overcomes this drawback is the Thomas flow meter or flow sensor. But it has also this idea that one heats the gas at some location, but one doesn't measure the heat drawn away from this heater, but one measures how much heat is transferred to another resistor while not being transferred to a second resistor upstream. So you can imagine that such a heater causes a temperature profile in this structure with isotherms, something like this. Yeah. So I'm drawing very schematically isotherms, and this should be a symmetric curve, so that this temperature and this temperature without flow is the same under this heating by delta T in the center. We have delta delta t left and delta t right. And for v equals 0, of course, delta t left is equal to delta t right. The sensors work. And now if gas flows, of course, more heat will be transferred to the right. So this isotherm profile gets distorted towards the right, so that delta t right will be larger than delta t left for V positive. And for V negative, the opposite will be true. Delta t will be right will be smaller than delta t left. So because this temperature profile is shifted to the left instead of to the right. And so this is the principle of many sensors, and especially hot cantilever, hot film. So there were cantilever sensors that exploited this hot wire anemometer principle. Yeah, hold a cantilever into the stream, heat it at the front, and measure its temperature, and then try to keep its temperature constant by adapting the heating power at the tip. That is a way to do that. So there are structures out there, but they suffer from this King's law behavior. Yeah? And then there are bridges and triple parallel bridges with heating resistors and temperature resistors. Like Honeywell has implemented them with platinum resistors, and Bosch has these sensors also to measure gas flow. So where is gas flow measured? In every engine. The intake of air into the engine is an important parameter to make the engine run optimally. To put the right ratio of gasoline into the air so that the explosion consumes all the gasoline and one has the optimal efficiency of the engine. And this will be still the case for a few years until we only have electric cars. But at this moment, it's still like that. And so any gas sensor, gas flow sensor, could work on this principle. Breathing resistors in the hospitals in Corona times to ventilate the lungs of Corona sick people used this kind of sensors to measure the amount of air injected into the lung and drawn out of the lung so that people wouldn't get any harm. That's a difficult problem because the lung tissue is highly sensitive, and we expand the lung by pulling it apart with our bone structure and muscles that can expand the lungs. So we're drawing air in by an under pressure, whereas these ventilators, they pump in air, and if that pumping is done at too high a pressure difference, then the lung tissue is damaged. It's better to avoid that. So Honeywell produced these sensors, which I can draw schematically. Let me just take an empty page to show you how these structures are done. Empty page. Not like this. Wrong reflex. Stop. Pencil. I want to put it in here. Yes. So imagine I'll draw a big chip, and then I'll draw a cavity, as you know it from. So this is the chip, and then we have this cavity realized by anisotropic etching. Yeah. Can you see that? Cavity? Yeah. Okay. Fair enough. Yeah. And now imagine instead of having this empty cavity, imagine this cavity to be crossed by a bridge. Yeah. So this bridge has, of course, some thickness, thin films. And then I guess I need to erase a little bit of material here. And so here too, and then this is also not visible actually. It should just be dashed. So maybe we have some dashed structures. And then some dashed stuff. And then you can also imagine another bridge to cross here and here. So let me also erase a bit here and here and here and here and here. So anyone see that? Probably this is wrong. I need to have some thickness, and then probably we also have some dielectric material, so that should also draw here. So and so these bridges, bridge, the central bridge. Okay, I can write here the thickness of the bridge also. This one is a bit thick here. So now we can have heating meanders, one going through here. So basically a thick heating meander through which a current is sent to produce some delta T central. And then here we have more heating meander, we have more resistor elements. So these are, with Honeywell, these are made of platinum and platinum. And the airstream now goes in this direction. So this beam will receive some heat from the central beam via thermal conduction. It will be heated up to delta T, let's call that left. And then this is delta T right. If we go from this direction, it's like going from left to right in this picture, from left to right in this picture. And I'm definitely on the wrong file. And so this, with increasing velocity v, this delta T will go down and this will go up. Now you have two resistors, one which goes down and the other one goes up under V. If I imagine now a response curve of the sensor as a function of V. So the difference of delta right minus delta left at velocity 0 is going to be 0. At positive velocities, therefore in this back direction, delta T will go up, so the signal will be positive, and vice versa if the flow velocity changes direction. So here you have a bidirectional flow sensor, which you cannot expect of the hot wire anemometer. It's insensitive of the velocity. So here we have a sensor that is dependent, that is direction dependent. And also it has this linear characteristic in the center because we are modulating a temperature distribution by transport. And that causes this curve to have a linear slope, which is much easier. And if now this is measured, the measurement signal, let's say the difference of the resistances, as measured in the Wheatstone bridge. I mean, these are two resistors. We have a resistor right and we have a resistor left. We can imagine those to be part of a Wheatstone bridge, R left and R right. Then kind of R0 and R0 identical. So a fixed branch having this this voltage that is being applied here and here volt out. no, or ground. And then and we can, at V0, the voltage difference here, this output voltage is going to be 0. And if the delta T, if those resistors, change resistance value because their temperature changes, then of course there's going to be an offset here, and that's proportional to that temperature difference, because resistors vary linearly with temperature at small temperature changes. So this is basically how Honeywell's sensor works, and Bosch has similar designs. And so this is basically the situation when Felix Meyer started designing sensors. Actually, I designed some of his sensors at the beginning of his thesis, so that he could have a steep start, and the outcome after his thesis, looked like essentially membrane-based sensors with a central heating resistor, and then thermal piles on the left and right. So the three constituent structures of the flow sensors are on the same membrane, but they are at a sufficient distance from each other, so that when no gas flows, we have this thermal profile that is symmetric around the central heating resistor. And when there is a gas flow profile, of course, this is distorted to either side, depending on the gas flow velocity. And you can see this schematically here in the temperatures. Yeah, of course, at the heating position, the temperature is highest, and then the temperature goes down to this location, and it goes further down to T0 at the substrate. So this level would be T0 here, and then with gas flow, the left thermal pile end is heated less, while that on the right is heated more. And that causes a temperature difference at these two ends here and here. Now you have two thermal piles which provide an output signal, and the difference of those output signals is what you want to measure. So what you do is you just put those two thermal piles, one after in series, or rather in anti-series. You subtract one of the voltages from the other. When you subtract their voltages, then without gas flow, you have the output voltage 0. And when now one becomes hotter than the other, that voltage minus the other becomes positive, or if the gas flow goes in the other way, the voltage becomes negative. This is a simple principle that turns this thermoelectric structure into this gas flow sensor. And so this was a very early design showing, how small they can be. I remember I was project leader of this European project, and so we had to produce some gas flow sensors very early, and then Felix Meyer was kind of a hands-on guy and packaged one of those and put a tube on it, and then I took this aluminum base plate with this little gas flow fixture and the sensor fixed in the middle on this into the plane. I was totally naive. I had this thick aluminum plate in my bag, and I had only carry-on luggage. So I walked in the train and said, "Oh my God, I have to go through security check. What's going to happen?" They didn't even see it. Aluminum is too transparent for radioactive. Not radioactive, for X-rays. So they didn't see it, and so I came to Brussels, and then I mounted my device and put it up, and I let the EU officer blow. And then he wanted to see the sensor. I said, "Here it is. I can't see anything." "Hey, this is a micro sensor." So fabulous memories. And we also produced some 2D sensors. Yeah, you can imagine this sensor only is responsive to one direction, of course, or bidirectional in along one orientation. But if you produce a structure that has a spatial symmetry of 90 degrees, then you might be able to produce a 2D flow sensor, which you can put in air. And then not only does it give you the velocity of the air over the structure, but it gives you also the direction of the air velocity. And so here's a structure that has that that property. So yeah, we see in more detail here. So here's a membrane version of such a sensor. It is heated in the center, and then it has 4 integrated thermopiles on its surface, each of which is read out. Now you can imagine that if the wind blows from bottom to top, what will happen? Heat will be carried more in this direction. So it will be hotter here and less hot here. I'm writing cold for less hot. Hot and cold. So you can read very directly the amount of heat transported in this direction. Those other thermopiles will have no output. Here we'll have an output, delta V Seebeck thermoelectric, proportional to this yellow arrow. And here we have thermoelectric voltage equals 0 because of symmetry reasons. And if there is a gas flow in this direction, of course, here we'll have delta V thermoelectric different from 0, proportional to Vx, whereas this is going to be proportional to Vy, and so with this structure you can determine the direction of the wind velocity. And then there was also crossed bridge design, with central heater and then thermopiles, like 2 membranes superposed on each other. This could also have been a square membrane, with sensors integrated, but this was to be etched from the front, and it's thermally even better insulated than a membrane, and the measurement principle here is the same as twice, in parallel, the measurement principle of the sensor here. So these were some early publications, and here is another design based on a bridge, with now here only two bridges, but the heating resistor in this sensor is essentially here along the inside of this one bridge, and then here along the other direction of the bridge. So well, it's also connected to the outside. Actually, it's connected here and then connected to the outside here. And then we have some additional temperature measuring meanders here on the outside. So the R left and the R right are here on these bridges, and this structure also enabled to measure the flow velocity in this direction, of course, or in the opposite direction. So when we look at these early results, then here you see an early package of these structures where one of those sensors was mounted in a ceramic plate with a square hole where the chip could be placed inside, and then the chip was bonded to the plate, and then a flow channel was led over that chip with some outlet here and some inlet here to let some gas flow over the surface. And this flow channel that you see schematically here is represented here in cross section. And the flow profile that you have in such a channel is of course well, it's not a constant profile, it's a velocity profile of parabolic shape if one is far away from the entrance of the tube. That is flow dynamics, it's a complicated subject, and then you blow in air from some bigger hose into this small tube, and at the beginning it has constant profile velocity over the cross section because of frictional forces on the surface. This parabolic shape, the Hagen, the Poiseuille flow profile, Poiseuille flow profile, which then gives its origin to the Hagen-Poiseuille laws of pressure flow for length of a tube. So the membrane is placed right flush in the surface of this tube, and you see here some isotherms with a 0 meter per second flow velocity, average flow velocity in this tube. And it's quite symmetrical, so that if you measured the temperature here and here with the thermal pile from one side and from the other side, you have the exact same signal. And when the flow is now sent over that structure, the flow profile is distorted, and then one has a less heated and a more heated point here, and that temperature difference is what is measured, as you know now. So this was just to visualize a bit the thermal situation in this flow channel. And Felix Meyer, of course, was very serious, and he measured these structures in tubes of various dimensions, just to see, how the dimension would influence the sensitivity of the center. And so it's quite apparent that the smaller the diameter of the flow channel, the more sensitive the structure is. And that is due to the fact that if the average velocity is the same, of course, that parabolic profile with average velocity identical to the original profile of this thicker channel has a much higher slope in this area. So for the smaller profile, this slope is going to be much stronger. Well, no, I should draw it like this. So the slope is much higher. It scales with 1 over the diameter of the channel, and that influences the profile as well. And that's what we see here, that smaller channels have causes higher sensitivity. And then I remember going to the wind tunnel of ETH Zurich, this big, massive infrastructure that was about as big as this hall. Big fans sending air through a sensor in the middle of this big stuck in the wind. And then we blew wind of very moderate velocities and Hauch up to 38 meters per second, which is actually a Beaufort 12. That's hurricane level. It's quite strong. And you see that the center basically was able to cover the whole range of velocities. And in this area here, we measured for very small velocities also sensitivity. So it was really able to measure very small velocities of the tubes in a non-linear characteristics, I have to admit that. But anyway, these sensors are what essentially are implemented in the products of Sensirion. This company in Schäfer, Switzerland, that produces these sensors for semiconductor manufacturing equipment, deep reactive ion etching equipment, where gases, well-controlled amount of gases are released into the pressure chamber to be activated by some inductive coupling to etch silicon. So semiconductor industry is one big customer of Sensirion's gas flow sensors, but also the medical instrumentation market is big. So these gas flow measurement systems were in operation long before COVID, but they really boomed during the COVID pandemic because all the hospitals had to have additional air ventilation, breathing control apparatuses. And then you see here an interesting, product. Felix Meyer, who's the founder of Sensirion, he didn't start his PhD with the idea of founding this company that would one day produce sensors for the medical business. He was one of those gliders, hang gliders with the gliding planes. I talked to you about these little clouds. I see some of them today. So there is Overbeck Bussinesque instability out there. And you could rise up high with your plane now. And so he flew one of those planes in Switzerland for his hobby. And so he wanted to have better flow sensors to say the speed at which he flies. And so he said, okay, let me build in my sensor into a little flexible PCB. That was also very new at that time. Nowadays, flexible PCBs are all over the place. But then it was really sensational. And then he mounted his sensor on this PCB and on a standard socket, and the standard socket was covered by this machined PMMA structure with a hole, and the hole is structured in such a way that the sensor is then right flush with the hole. And so whatever wind blows around that structure, so around that structure and through the hole and out again at the other end can be measured by the sensor located at this central position. And so he was able to make measurements, indeed. And then he thought, okay, can I also do what will happen if I rotate my structure? Obviously, if I'm perpendicular to the wind direction, I should measure nothing because both holes are equally likely of collecting wind, and so nothing will flow through. And if I or in 180 degrees, I should have the flow in the opposite direction. And so we were surprised to see that the response was actually, let me say this is a positive signal. It says absolute value of V out. So this is now positive. And then as the angle, so this is really, the wind is now blowing right into the channel. And then, so the wind comes in this, this is the wind direction, V. And now as this tube is rotated around its angle, instead of going through a simple zero and then crossing over to the negative value, so let me draw that in Cartesian coordinates. New tab. Well, I wanted to erase this, and draw something black. So let me draw this as a function of angle. Let's call this angle 0 degrees. And then alpha is measured in this direction. So here is alpha, and here is 0 degrees. We have some positive signal, this one. And then obviously there is 90 degrees and there is 180. And then boop, boop, we come to 360, we should be back to the origin. But anyway, at 180, we expect definitely a value at the same position, but in the negative. There's no doubt about that. So my expectation was that if we turn around the sensor by 180 degrees, the wind blows the other way direct through the channel, and then we have the negative signal. And then we also know that at this location, at 90 degrees, there must be signal 0. So what else simple to expect than a cosine response? But that's not how it works. flow dynamics around cylinders is more complex. We know, yeah? The mechanical engineers, the aerodynamicists know that. Yeah? And so there is actually an angle where you go through zero, and then you go again through zero, and you go again through zero. Yeah? And that's what we measure is actually the pressure difference, the delta P. Yeah? The delta P on a cylinder. So if I look at the cylinder from the top and my wind comes here, yeah, I will have a pressure difference between opposite points. Yeah? And these opposite, no, let's make some different symbols, yeah? Opposite points. Yeah? These pairs of opposite points produce pressure differences, and the pressure difference drives the flow through the channel. So if the channel is in this direction, okay, then there will be flow. But it's the pressure difference that drives the channel. And the pressure difference of points that are close to 90 degrees, somehow for some flow dynamic reason, because of some backflow or whatever, is caused to take the opposite value that you would simply expect. And so this is what comes out, and this is in polar coordinates, a curve that goes here and then around this corner, and then around this corner and around this corner, and then closes here, with positive and negative loads. So actually, it goes from positive to minus, and then to positive again, and then to minus again, and then to positive again, and then go back. Yeah, so it's kind of a complicated story. Yeah. But Felix discovered some flow dynamics books that describe that phenomenon actually. Yeah. So it's really the pressure P as a function of angle alpha, and then P of angle alpha, P of alpha minus P of pi, or alpha plus pi, that is proportional to the output voltage of the sensor. Yeah, and so final slide of this chapter, some flow meters I picked from the website many years ago. Yeah, so this is basically an instrument that can be hooked up to some hoses, and then will measure the flow through this orifice. And actually, it's not the velocity; it's the mass flow, the amount of gas mass that flows. When one knows what the gas is, these flow meters are not mass flow meters really, but you can use them in operation modes where you can also detect what is the density of the gas, and therefore get independent of the gas. And then they expanded from this original gas flow to liquid flow. Yeah, now that's a problem because of course liquids easily experience pressures that exceed a lot of critical values that will be deleterious to these delicate membranes. And so I know that they started mounting the sensors directly on very thin steel tubes. So at the outside of a steel tube, with a very thin wall, so that the heat of the sensor is carried by the steel tube via also the steel tube to the measuring points of the sensor, the ends of the thermal points. And when the flow flows through the steel tube, not in contact with the sensor, but only with steel, then heat is also transported. And this is how medical grade devices are made, because you cannot let a patient breathe something that crosses over a technical surface like a microsensor. It has to be some EC validated material. That steel is definitely the case. Yeah, so this is meant by heating and sensing through capillary wall. The transport within the capillary transmitted through the wall from the sensor to the capillary, the inside of the capillary, and then out again through the wall. And this is used then in control systems. One is not only interested in V, one is interested in controlling the volume of gas, or the mass of the gas that goes per second. And then these flow meters are combined with some valves that regulate in a closed loop the amount what crosses the channel to a given desired value. Yeah. And then you can also do differential pressure sensors. Yeah. So, but so if you would like to have, you have some pressure at one location P and some P0 at another pressure location, you can of course measure. You just connect the two locations with a tube, yeah, and then the pressure difference makes the flow. That flow can be measured, and so this is the principle of all differential pressure sensors. That there's this pi P and this P0, the low pressure, or P1, and then one would like to know the delta P equals P1 minus P0. Yeah, it is measured by the flow that is caused by the pressure difference. Sometimes you have these big, vessels, so you only need a very small duct to connect to the sensor. There's minimal volume extracted from these vessels at pressure 1. That's how it's done. Yeah, and with this, I'm at the end of this chapter, thermal sensors, and I will compile some exercises now on that content of this chapter, and we'll upload it hopefully by tomorrow morning, and then we can talk about it next Tuesday, I would propose. Next Monday, I will teach on inertial sensors, and then we can have Tuesday the discussion of these exercises, the thermal exercises, and then we can talk about the end of inertial sensors in the last week of the semester. Yeah, for that, thank you for your attention, and looking forward to next Monday.